The mysteries surrounding black holes have long puzzled the minds of scientists and ordinary people alike. These mysterious planetary objects, characterized by their ability to capture everything in their orbit, including the moon, represent one of the wonders of the universe. A black hole forms when a supermassive star reaches the end of its life, collapses under its own energy, and becomes so massive that its escape velocity exceeds the speed of light. As a result, nothing, not even electromagnetic radiation, can escape. For decades, black holes were commonplace, predicted by Albert Einstein's general theory of relativity. However, the use of advanced observational instruments such as the James Webb Space Telescope has opened up a new era of understanding, revealing unprecedented aspects of the dynamics and behavior of black holes. Black holes are generally classified into three types: stellar black holes, supermassive black holes, and intermediate mass black holes. Interstellar mass black holes form when stars of high mass run out of their main fuel and collapse. The mass of these black holes is usually between 3 and 10 times that of the Sun. On the other hand, supermassive black holes are at the center of most galaxies, including the Milky Way, and have millions to billions of times the mass of the Sun. Their origin and formation are still the subject of much research, but they play an important role in shaping the formation and evolution of galaxies. Intermediate mass black holes, although suspected, are more difficult to detect and study due to their relatively invisible nature, lying somewhere between the mass of stars and supermassive black holes. The first black hole, Cygnus X-1, was discovered in 1964, marking a major breakthrough in astrophysics. Prior to this discovery, scientists such as Stephen Hawking and Kip Thorne had speculated about the existence of these invisible celestial bodies, but had not collected proper observational evidence. Cygnus X-1 is located 7,200 light-years away in the constellation Pisces and is part of a binary system. It emits powerful X-rays when it ejects material from a nearby massive star, revealing its presence. This important discovery was made possible by 2 Geiger counters launched on a suborbital rocket, which detected intense X-rays from the region where the black hole is located. Hawking and Thorne made a famous bet about whether Cygnus X-1 was actually a black hole. Although it was close to 100% in 1975, they waited until the 1990s to prove it, admitting that more evidence had been collected. Cygnus X-1, which has about 21 times the mass of the Sun, challenged many assumptions about the formation of black holes and the loss of mass experienced by stars during their lifetime. Its rotational speed, approaching the speed of light, has further defied long-held theories regarding the evolution of black holes, solidifying its status as one of the most important objects in black hole research. At the heart of nearly every galaxy lies a supermassive black hole, a cosmic behemoth whose gravitational pull helps shape the destiny of its host galaxy. The Milky Way's own central supermassive black hole, known as Sagittarius A*, is approximately 4 million times more massive than the Sun. While supermassive black holes are crucial to understanding galactic dynamics, one of the most pressing questions in astrophysics remains: which came first, the galaxy or the black hole? This cosmic chicken or egg problem has yet to be definitively answered, but researchers are making strides in understanding how these gargantuan entities influence their surroundings. One of the most important things about supermassive black holes is the formation of quasars. Quasars are very luminous objects that work with accretion disks, balls of gas, dust, and stellar material that fall into a black hole. As the material moves in, it burns to extreme temperatures and emits energy that can spread throughout the galaxy. These quasars, visible from billions of light-years away, act as beacons for supermassive black holes in the early universe. Close-up observations from the James Webb Space Telescope, JWST, have revolutionized our understanding of supermassive black holes. The most famous discovery is the discovery of a supermassive black hole about 12.9 billion light-years from Earth in a quasar that formed 700 million years after the Big Bang. This discovery challenges current models of black hole formation and shows that supermassive black holes can form earlier and faster than previously thought. Another major advance in black hole research has come from the discovery of spin waves. These ripples in space-time, predicted by Einstein's theory of general relativity, are created by the acceleration of massive objects such as colliding and merging black holes. In 2015, The Laser Interferometer Gravitational Wave Observatory, LIGO, made history by detecting gravitational waves from the merger of two black holes, each about 30 times the mass of the Sun. This discovery confirmed the coexistence of stellar mass black holes and opened a new way to study these objects. Since then, many simulations have been made, showing the entire population of merging black holes. The cosmic rays provide valuable information about the mass, spin, and dynamics of black holes, allowing scientists to observe them in ways never before possible. In addition, the study of these waves led to the discovery of medium-sized black holes, which until recently had been proposed but not confirmed. These observations have revolutionized our understanding of black holes and their role in the universe, providing new insights into the behavior of these cosmic giants. Microquasars, a smaller form of quasars, are black holes that enter a binary system and eat food from a companion star. When material is pulled into the black hole's accretion disk, some of it is ejected as a relativistic jet, a stream of particles moving at nearly the speed of light. These jets are of particular interest to scientists because they act as natural particle accelerators, producing electromagnetic and gamma rays visible from Earth. One of these microquasars is SS 433, located in the Milky Way. The study of microquasars provides important insights into the interaction between black holes and their surroundings. Although SS 433 is the most famous example, there are likely many other microquasars scattered throughout the universe, contributing to the universe's population of energetic particles. By studying these properties, scientists can better understand how black holes affect their surroundings and drive some of the most powerful phenomena in the universe. Although most black holes result from the collapse of massive stars, some may have formed in the early universe, shortly after the Big Bang. These so-called primordial black holes are thought to have arisen from density fluctuations in a hot and rapidly expanding universe. If primordial black holes exist, they could provide important clues about the nature of dark matter, which makes up 85% of the matter in the universe but is still missing. Black holes tend to be smaller than stellar or supermassive black holes, which can range from the size of an asteroid to several solar masses. These items are hard to find due to their limited size and limited availability. However, their presence may help to explain some of the mysteries surrounding the dark ones. If primordial black holes are part of dark matter, their discovery could solve one of the biggest problems of modern astronomy. One of the most enduring mysteries in black hole physics is the information paradox, a theoretical problem arising from a conflict between quantum mechanics and general relativity. According to general relativity, matter that falls into a black hole is lost forever, trapped outside the event space. However, quantum mechanics believe that information cannot be destroyed. This contradiction has led to a decade-long debate among physicists about the fate of matter that enters a black hole. In the 1970s, Stephen Hawking proposed that black holes could emit radiation, now known as Hawking radiation, due to effects of sizes close to the collapse zone. Over time, the black hole loses mass and eventually collapses. But if the black hole shrinks, what happens to the information inside? Do they disappear when the principles of quantum mechanics are violated, or are they preserved? Recent advances in quantum information theory and holography have provided new solutions to the information hypothesis. Some theories suggest that the information will be stored in a highly volatile form at the event site, while others suggest that it will be incorporated into the radiation emitted by the black hole. Although the paradox remains unresolved, it remains a subject of research and has profound implications for our understanding of the fundamental laws of physics.